Hi, Nishad, can you hear me?
Yeah, good morning, Professor Jamal. We can hear. So I would welcome back. I would request all the participants to pose the questions at the end of the session, not in between. If you want to ask any question, please pose the question in the chat box, and later on it will be discussed at the end of the session. Thank you. Professor Jamal, I welcome you and all the participants for the last session uh, of this program for today. Uh, please continue the session. Thank you.
Thank you, Nishad. Um, Good evening, everyone. So today I am going to talk about plasticity. So you probably know about plasticity already, but I am going to, I guess, challenge you about theory of plasticity. I'll look at it from a different perspective. Now, in the first two lectures, we discussed the unified mechanics theory, where you have laws of Newton and then laws of thermodynamics. So in the traditional theory of plasticity, the stress-strain diagram that we get from testing and use as a material property is governed by laws of Newton. You take a new sample, test it, and then you have stress-strain diagram. But however, there is nothing scientific behind it. Okay, it is not based on any scientific calculation. You can do dislocation dynamic or molecular dynamic analyses, but in molecular dynamic analysis, number one, your time is limited to less than 1 femtosecond, or very, very small. So it is not a equilibrium state. And number two, you are limited with few atoms. So it is not a real life case. So the material behavior we obtain is completely empirical. Now, so what do we, first of all, what do we say, what do we mean by plasticity? That is the important thing. Now, we say if we take a sample and apply it uniaxial tension, according to this theory, there will be in it, these represent the atoms, these pink colored balls represent the atoms. And then when we stretch it, initially the distance between the atoms will stretch. But however, if we let the load go, it will come back to the origin. There will not be any permanent deformation in the material. This is what we assume. And then if we increase the strain on the sample beyond a critical stress level and then go up, as a result, the material will deform. There will be groups of atoms sliding over each other, just like if you have a deck of cards, like what you use for gambling the cards. And then if you subject them to shear, some group will slide over the other group. And then when you unload, get rid of the load, they will not go back to their initial state. So this is the basis for theory of plasticity. Of course, in real life, in the elastic zone, the atoms do not go back to their initial site. Because if they did go back to their initial site, then that would violate the second law of thermodynamics. Because if you applied energy from outside, you bring the material to a different state, and then you let it go back, it cannot go back to the same order. The order will change. It will be another disorder state. Where do they go, the atoms? Always there will be another site where the atom would be at a lower energy state. It will have neighbors from all sides. Now, of course, in this picture, one thing is not true. The sample has no defects. There are no missing atoms. If there are no missing atoms in the system, theoretically, you cannot have any change in disorder because there is no site to go to. But always there will be defects. So essentially, if there is no nature, in the nature, if we did not have any defects, it would be very, very difficult to generate entropy. As a result, the system would live forever. It is like, look at it this way. If you are born and you have no genetic defect whatsoever from day one, okay. And then when you get old, nothing can essentially get sick because everything in your system works perfectly. You can get old, but you cannot die. So you, okay, somebody has to mute.
Can you mute Venkat Rao, please?
Somebody has to mute in between.
I think you can mute them, Nushad.
Host is Mr. Ashish.
Huh?
Yeah, I request Ashish to.
I have muted.
Oh,
muted.
Ashish is the host?
Yeah, thank you.
Sir, I have muted.
Oh, okay, okay, no problem. So therefore, for the plasticity to happen, there has to be a defect in the system. If there is no defect in the material, there cannot be plasticity because this movement is happening along the dislocation slip lines. Now, so we define yield stress as at which noticeable plastic deformation has occurred. But that is a very arbitrary definition. That means that's something we can measure. That doesn't mean that there is no plastic deformation before we can measure. So we assume that strain, if the plastic strain is 0.002 and corresponding stress value is the yield stress. So if you are looking at a 2-inch sample, it is very, very small deformation. But actually some materials start yielding from the very beginning, like aluminum, copper, gold, polymers. So the concept, this concept of yield actually is only valid for materials with metallic bond. It doesn't really make sense for a covalent bond or ionic bond materials. So this is something my students always get confused about. So if we introduce 0.02 meter plastic deformation to a 1 meter long steel rod by stretching it beyond its yield, as a result, the new length is 1.02 meters. Then we decide to return it back to its original length by pushing it back to 1 meter. So essentially, it's just like a linear elastic system. At the end, the bar has the original length. So final length is the same in this process. So what would be the plastic strain for this bar? Can you write your answer in the chat? You know, strain is deformation 0.2 meters divided by 1, right? You can assume that there is no elastic deformation. So what would be the plastic deformation in the final sample, final bar, which is I start with 1 meters, I finish with 1 meters. So I'm waiting. What is the plastic strain in the 1 meter long steel rod at the end? I have only one answer. Well, I'm waiting. I'm not going to continue unless you give me answers. I want to know what you guys think. That is important. If you don't want everyone to see your answer, you can just send me your chat. You don't have to, you can change the two to just me. So nobody will, I need a number though, not a tension compression. What is the strain in the final bar at the end of the experiment? I start with a 1 meter long bar. I finish with 1 meter long bar. Is there a strain in this bar? Well, you don't need the yield stress because I am giving you the amount of plastic strain. It is 2 centimeters. I stretch it by 2 centimeters in tension, and then I push it back in the compression 2 centimeters. So I start with 1 meter long rod, finish with 1 meter long rod. What is the strain? So essentially the initial length of the rod and the final length of the rod is same. Okay, I'm still waiting answer from others. So there are 40 people here. How many answers I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The answer is not yes or no. I need a number. Somebody said yes, but I need a number. Just give me a number. Just give me a number, what you think. Is the experiment I'm explaining clear, or shall I do it again? Okay, some people are signed up, but I think they are not here. That is what I will assume. Okay, so the plastic deformation means that it is irreversible. Okay, it is irreversible. You created 2 centimeters divided by 100 centimeters initial plastic strain in tension, and then you add the compression one in negative, but there is no negative strain, plastic strain. It's always positive. As a result, the total strain here will be 4 centimeters divided by 100 centimeters, so it will be 4%. The length of the bar will be same as the initial length, but the bar will be in 4% plastic strain, because plastic strain is irreversible. Okay, this is similar to example I gave you yesterday. You know, if you look at these Hollywood movie stars, musicians, sometimes they're 80, 90 years old, and then of course they have a plastic surgery every year. They look like someone 30 years old. From outside, they look like 30 years old, but then they die next year because the deformation in the system, degradation is irreversible. What you see doesn't matter. The irreversible process is what matters. So plastic strain is irreversible. So for the plastic strain to happen, you have to have, as I said, defect in the system. If there is no defect in the material, there cannot be plasticity. You can only have elasticity. We call the linear defects dislocations. These are line of missing atoms, or they can be an edge dislocation, shape, or screw dislocation. They look like this, like each blue circle here represents an atom. So for example, in this row, I have 7 atoms. So these atoms are in good order. Here I have 7 atoms. But however, in this row, I have 6. So 1 atom is missing here. As a result, there will be what we call dislocation here. And of course, as a result, the atom between these 2 atoms will be under strain, because here they are in their equilibrium spacing, but here they cannot be in equilibrium spacing because there is 1 atom missing. So we call this row of atoms missing edge dislocation. And then I don't think this will move here. It was actually a video. And then if it is, when it is subjected to shear, this group top section will move with respect to the lower level along a what we call a slip plane. Now, the screw dislocation is essentially you have this lower cube is twisted, or the upper cube is twisted with respect to the lower cube. And that defect is called the dislocation, screw dislocation. And it looks like this. And of course, most of the time you have edge dislocation and screw dislocations at the same time. You have, now this is for metallic bonds, and dislocation motion is easier because metallic bond is non-directional bond and closed pack. And the electrons don't belong to, valence electrons don't belong to any of the ion cores. So it is very easy for these atoms to move along any slip plane. But when you have a covalent bond in ceramic, okay, you don't have these free sea of electrons. They share their electrons. So the motion is very difficult. Only way this can move someplace is it has to break bond with all neighbors. So as a result, ceramics are very brittle materials. They don't bend. And then same is true for ionic bonds, because you don't have, again, free sea of electrons. The charge prevents it from moving. As a result, plastic deformation is more difficult because they share their electrons between two atoms. Here, everybody shares everybody else's electrons. So essentially, if you have this sample, this will be your slip plane. If you subject it to shear force, so we hold it from here and then apply shear, this block will move along this line. Well, you might say, why doesn't it break from here? Well, because here you have 7 bonds, 1, 2, 3, 4, 5, 6, I'm sorry, 6 bonds. And here you have 5, 1, 2, 3, 4, 5. It is easier to break 5 bonds than 6 bonds. And then this block will move 1 to the right, and they'll make new bond with new neighbors. And then finally, this piece will come out. Because atoms want to exist at the minimum energy state. Like this atom is in minimum energy state. It has neighbors in each direction at the equilibrium distance, and there is no strain or stress or force on this atom. In nature, everything wants to exist at the minimum energy state. So there are many slip systems at the atomic level, so in 3D, and it is easy to formulate this process in a single crystal level. But however, there are billions of trillions of atoms, trillions of dislocations in the system. As a result, we have to do macro scale testing to get the properties, because so far we have not been able to model the system as a thermodynamic system and then analyze it and then calculate the stress strain response. So for a single crystal, we just say when the critical stress, shear stress level exceeds a critical value, this resolved shear, a critical value, this block will move along to this block. So in plasticity, we need several things for plasticity to happen. Number one, there has to be a defect in the system. If there is no defect, there cannot be plasticity, number one. Number two, there has to be a shear stress. If there is no shear stress, there cannot be plasticity. So if I take a system with defects, but just put it under the water, 10,000 meters under the water, hydrostatic pressure, there cannot be any plasticity. There has to be shear stress. And then the shear stress value has to exceed a critical value to break the bond between the layers. But it is what we call yield stress at the macro level. And of course, the motion of dislocations, the stress on the system can be calculated from just simple transformation equations easily. So this is the resolved stress, tau R, tau C, RRS is the resolved critical shear stress. So these are, now this is a picture, picture from a microscope, a single crystal subjected to uniaxial tension. And then you see these are the slip planes in the material. Now, what we observe as a plastic strain or change in length, actually, it is just a motion. Like if you think of it, you have the diameter here, okay, and the length is initial length, and then these blocks move with respect to each other and then you think it is longer now. Actually, you measure it as longer because there is a relative deformation. It is like if you take a deck of cards, now the length of each card is constant, and then you apply a shear load to this deck of cards, the new length of the entire card system will be longer, but the actually length of each card is still same. So you observe it as a longer because they slipped with respect to each other. So that is how it looks like under a microscope. And we can do these calculations for a single crystal, but of course we do not have single crystal system in real life. We have polycrystals. I would like to show you, jump to this polycrystal picture. So each organized section, you see in this section, lines are parallel to each other, lines are parallel to each other. That means that is one crystal, because within one crystal, atoms are aligned. And then here you have a grain boundary, there is another crystal here, and these atoms are aligned in this line. Here you have another crystal here, these atoms are aligned along this line. So most of the time in metals, we have polycrystal. And these straight lines that you see are defects, the dislocation lines. When you apply shear, the layers will move with respect to each other. But of course, they will also try to cross over these grain boundaries, which they make it difficult to move. As a result, having more grain boundaries makes it more difficult to move for the dislocation. As a result, yield stress will be higher. So a material with smaller grains will have a bigger yield stress. And of course, we can have anisotropy in different directions. We can have different yield stresses. But we can have introduce anisotropy by loading the system. Like after rolling it, grains change their shape, and now their yield stress will be different in each direction. Like the rolling that we use, for example, to make automobile bodies or any steel stamping plant. Now, if the material is anisotropic, for example, here is an anisotropic material, you fire a cylinder at a target. Now, this is a rolled plate, but the sample is cylinder. But however, it was rolled. So the bullet was made after rolling it. Now, if it is isotropic, the deformation of this bullet should be circular here. But instead, after you fire it, the bullet ends up with it doesn't have a circular shape. It has an ellipsoidal shape because it doesn't have the same properties in the, let's call X and Y direction. So, of course, by changing the grain size, we can increase the yield strength, or adding solid solution, which mixing it, or compression, because of course we have stress concentration at these dislocations, and then we can strengthen the system by essentially using fillers. Now I want to go to another, I'm going to stop my sharing. I want to go to a different presentation. What this plasticity? No, not this one. Now, 1 second. Let's formulate this plasticity. So just here, okay. Oops, sorry. Okay. Okay, let me share my screen again. Now, this plasticity also introduces something called length scale in materials. What does length scale mean? Length scale means that it's easier to explain it here. Now, I test a sample. This is a beam, okay? Tin film. Oh, I'm sorry, this is a torsion experiment, okay? Micro torsion experiment of copper. This is the stress normalized for volume, megapascal, okay? And then these are for different diameter wires, copper wires. So for example, for this red one, 12 micrometer diameter, this is the, you can think of this as stress strain diagram, okay? It is normalized, but it is still megapascal. And then 170 micrometer diameter wire is here. So what happened is, we said we are getting stress strain diagram to give us material properties. But when I change the dimensions of the sample, I am getting completely different stress strain diagrams. And the difference is not small. We are talking about here 200 and here close to 700. This is called length scale. Okay, so our theory of plasticity applies if the system is bigger than a representative volume element. If it is smaller than a certain size, or the strain gradient is very large in the system, then the theory of plasticity formulation has to change. Here is another example for micro hardness testing. Here is another for micro bending nickel tin film. This is the normalized moment applied on the tin film, the moment, the maximum moment on the, it's a simply supported tin film. So it is, you can think of it as a simply supported beam. So the maximum moment is in the middle. So this is the moment. And this is the surface strain. And this H is the thickness of the tin film, the thickness, uniform thickness of the beam. So when the beam is 12.5 micrometers, you get these data points. When it is 50 micrometer, you get these data points, completely different. As a result, this has to be represented in our formulation. So that means I cannot use traditional theory of plasticity, because theory of plasticity does not have a term for length of the size of the sample. The way we introduce this traditionally, because we consider yield stress is proportional to dislocations, but then when there is a length scale, those dislocations are called statistically stored dislocations. These are the regular dislocations that we know from theory of plasticity. But when length scale becomes an issue, then we call the additional dislocations as a geometrically necessary dislocations. These dislocations are created in order to accommodate the deformation. As a result, the smaller the sample, it will have a higher strength, stronger. So, for example, let's go to simple Taylor's law for yield stress or flow stress, whatever you want to call it. This is, of course, true only for a single crystal, right? Here, rho is density of dislocations, B is Berger's vector, mu is shear modulus, alpha is empirical coefficient, which we obtain from testing. Why we need alpha? Again, because we said theory of plasticity is an empirical theory. It is not based on science. It is not based on any direct physical mathematical calculations. Why? Because we don't have the mathematical formula and we don't have the tools to be able to do the calculation. So we do an experiment to get this alpha. Now, when the sample becomes very small, we modify this dislocation density by adding rho g, geometrically necessary dislocations. So as a result, the flow stress becomes, in the classical plasticity theory, flow stress or the yield stress is a function of plastic strain, which is a function of the statistically stored dislocations. Now, when the length size of the sample gets into the picture, because our system is smaller than the representative volume element, or the gradient is very large, then we use strain gradient plasticity theory. The yield stress is a function of plastic strain, and then length scale of the material, and then another factor, which is derivative. This term is derivative of strain. Strain is derivative of displacement. This is derivative of strain. So that's why called strain gradient. So this is term coming from the strain gradient. Now, there are many theories to handle this strain gradient plasticity. One of them, or maybe the oldest one, is Kosarat continuum. Now, in regular continuum, if you take a stress point, these shear stresses balance each other. So as a result, if this is y and this is x, tau yx is equal to tau xy, right? So that you can satisfy moment equilibrium with respect to the center. In Kosarat continuum, they are not equal to each other because there is additional moment on the system at the point in addition to the stresses, and these are called distributed moments. This is called Kosarat continuum, where tau yx is no longer equal to tau xy. So essentially, this is the classical theory, this one, but now we also have moments. in addition to surface tractions, which we have in the classical theory, we also have surface moments. Mij is the distributed surface moment. And as a result, shear stresses on the faces are not equal to each other. So when we write the formulation, the general theory, now the relative strain, if you have this is our traditional continuum strain, right? And then this is the relative strain. But however, now I have rotation in the system because of the moment. As a result, my energy term, which I use to solve for finite element method, the classical plasticity will only have this term, constitutive matrix, strain tensor. But now I have gradient of strain, a new constitutive tensor. And then of course, this is the surface tractions, and this is the surface moment. So this is the how we formulate if there is a length scale effect on the system. So I'm gonna stop here and then stop sharing, and then let's go to your questions and discussion. Okay, so let's start with the questions from here.
Hello, sir.
Sir, we don't get you, please repeat. Okay, sir, we don't get you, please repeat. What is that you don't get? I don't know.
Sorry, sir. I understood what I actually I was 4% total strain. What I was asking, that I got it.
Oh, the plastic strain is 4%.
Yes, sir. Yes, sir. I got that solution. No problem. I had a doubt. We have shown slip lengths in a micrograph.
I'm sorry, what did you say? I didn't hear you.
Slip lengths in one of the microstructure, right? One of the micrograph.
Slip, yeah, we have slip planes, yeah.
Yeah. Whether they are the slip planes or twin planes, do we have any way to distinguish them?
Well, if you use a microscope, yeah. I mean, distinguish them in calculations or distinguish them
by observation
in the microscope?
By observation. Microscope.
By observation, yeah. There are people who only their entire professional career is trying to see dislocations using microscope. They have their own conferences and everything, yeah. Okay. It's a field by itself.
Okay. I had a doubt whether it is a slip plane or a twin plane. So that's what I was asking.
Yeah. Okay, any other questions? Okay, I guess this is not as interesting as unified mechanics theory. That's why you don't have questions.
Sir,
okay, yes, do you have a question?
Okay. Yeah, I mean, I was wondering if there exists any substance or rather material which does not have any imperfection in it. Will that be a material which will never fail?
No, material will fail. You can always break the bond between the atoms, but we are saying that there will not be plasticity. There will not be permanent deformation. It will fail by just breaking the atomic bond between two sections.
Okay.
The atoms are, okay, let me. So you have two atoms here, okay? Two atoms here. And they are connected to each other with a potential. Now, if you move them apart, they will get pulled to next to each other. If you get past that critical point, they will push each other. And there's a critical point they will be at the minimum energy level. There will be zero stress force on the atom. Now, but that bond can be broken by applying a bigger bond, bigger force. So you can always, but however, there cannot be a plastic deformation. Like, for example, let's say take a piece of glass, okay? And there's a glass in your house. In room temperature, you couldn't bend that glass, it will just break. But if you heat that glass to 200, 300 degrees, you can bend it like a piece of rubber.
Okay. Okay. So what I understood is that plasticity is different from failure. I mean, they are different concepts.
Yeah, plasticity, the theory of plasticity that we discussed now is actually only true for metals and metallic bond materials.
All right. All right.
And it is a completely phenomenological theory. Anytime you have to do experiments in order to get the response, that theory is phenomenological, empirical.
Okay.
But hopefully you
Thanks.
guys will do research and then develop a thermodynamic-based theory where you can actually calculate the material behavior based on physics, which we don't have right now.
Yeah, I mean, you have definitely sown the seed for, especially particularly for me, because I was not aware of this theory, unified mechanics theory, before. I mean, it's really interesting. I need to explore it more.
Yeah, the traditional theory of plasticity is just a curve fitting method. Okay, you have these tons of constants, coefficients for yield surface and for hardening function, isotropic hardening, for kinematic hardening. And every time you are doing curve fitting, in my book, that is not science, that is just curve fitting. Any other questions?
Sir, just based on the previous question asked by Shravan, so you have given an example where you pull two atoms apart, something like a perfect crystal, and you pull it apart so that it breaks after a certain point. So now this deformation, what is happening during the process of pulling it, is elastic, right? So in that case, how do we calculate entropy there?
Oh, okay. So the theory of elasticity assumes that there is no entropy generation. If you pull two things apart, they'll go back to their initial location, which violates the second law of thermodynamics. Because according to second law of thermodynamics, if I do this X number of times, finally it will break. It will fatigue. So Xiaowei Li is going to give a presentation on that on Tuesday. So I don't want to steal his show. I will let him handle it. And this is his PhD, so he will do a very good job. So in the elastic process, actually, there are many dislocation. I'm sorry, there are many entropy generation mechanisms. There is nothing elastic. Everything is inelastic. Not inelastic. I mean, everything is irreversible. Everything is irreversible. Like you go home today, come back, you might think that nothing changed in you, but actually you are one day older.
Yes, sir. I'll wait for his lecture. Thank you very much.
Can Young modulus be determined by theory? Yes, Young modulus can be determined by theory, and then you can do molecular dynamics simulations to get the Young's modulus. We do that all the time. But the problem is, let's say, for example, concrete or steel or whatever material. It has many defects. As I said, the Young modulus for steel that you buy for $1 a pound or $100 a pound are not going to have the same Young modulus because, yeah, sure, they are both same atom, iron, but they will have so many defects, voids, crap, other elements in it, because it is not pure, right? Because they don't extract iron from the ground, they extract an element that is mixture of many things, and then they clean it. And then if they are going to sell it for $100 a pound, they purify it and purify it and purify it and purify it. If they're selling it for $1 a pound, they just give it to you after maybe one step. So therefore, the numerical calculation has to represent the defect density of the system that you are analyzing. But calculating the elastic modulus is easy, because it is the first derivative of the atomic bond potential versus interatomic distance curves first derivative. Any other questions?
Sir, my question is on the force balance that you showed on an element, right? And you said that the shear stresses are not equal. Tau y, the yx is not going to be equal to tau xy.
In Kosarat continuum, yes.
Yes, but so the if the stresses are not equal, essentially there is rotation. So stress would I mean the stress has to match, that the element would start rotating. I guess that is
Yeah,
what would happen.
element is rotating, but there is also additional moment applied on the system, and then the moment is balancing it.
Okay.
Yeah, there's a moment balancing that unbalance.
All right.
Sir, I have a question, sir.
Yes, sir.
Sir, is there any in real life, is there any material which perform like elastic, perfectly plastic material?
Elastic, perfectly plastic material?
Yes.
Yeah, there are many materials that behave elastic, perfectly plastic material, but the plastic is an idealization, is not a realistic material behavior, because plasticity assumes that time-dependent deformation doesn't exist. If you keep the load 1 day or 100 years, the deformation is still the same. But actually, for most materials, even the glass in your home, it will get thicker at the bottom after 10, 20 years. So theory of plasticity is a very, very crude idealization. Like, for example, we assume that for steel design, the steel joint behave elastic, perfectly plastic. But of course, they are not. There is hardening. But at the very high elevated temperature, probably steel might behave elastic, perfectly plastic at 600-700 degrees Celsius.
Thank you very much.
You're welcome.
Sir,
Yes, sir.
I mean, I know that advanced finite element method is put to use to find the solution of partial differential equation, and the solution that we get is, I mean, approximate, but it's very close to the exact solution, depending upon the nature of the mesh you are using and the safe function you are using. So I wish to know if unified mechanics theory has a role in that direction. I mean, finding the solution to these differential equations.
Well, unified mechanics theory is nothing special, just unification of laws of Newton and laws of thermodynamics, when in traditional finite element method, you only have laws of Newton and you don't have laws of thermodynamics. Like, for example, if you calculate the deflection in a bridge using finite abacus, it will give you the same deflection if the bridge is 1 day old or if it is 500 years old, right? It doesn't make any distinction between 1 day old or 500-year-old bridge. But if you use the differential equations from unified mechanics theory, it will depend how old the bridge is, because not just the nodal displacement is unknown, but also the entropy generation rate at each step is unknown. So when you apply a load, you don't just generate displacement, but you also generate entropy.
Mhm.
And then that entropy generation ages the stiffness. And then you, after 2 days or after 5th application, your stiffness is different. So the differential equation in unified mechanics theory has both the Newtonian differential equations and the thermodynamic differential equations. And at the end, you still put them in a finite element code to analyze the system.
Okay. Thanks a lot for the important
welcome.
insights, sir.
Sir, one probably unrelated question, but for example, material like shape memory alloy, nitinol. So you can have plastic deformation, and again, when you heat it, it goes back to its original shape.
Yes.
Now, in this, how do you explain using unified mechanics theory?
Yeah. So, well, before I answer the question, Nishad posted something in the chat. If you guys want to keep in touch with us after this workshop, we have a group on LinkedIn. It's called Unified Mechanics Theory Group. If you become a member of the group, we will be able to keep in touch with each other after the workshop. And then you can just click on the link Nishad put in the chat. Now, to answer your question, so let's go back to the sample that I gave. I have 1 meter long bar. I apply tension, and then I introduce positive 2% plastic strain, and then I push it back. I apply negative 2% plastic strain. So I have 4% plastic strain, right? Because it is an absolute addition. And then I take this bar, I heat it and anneal it for X amount of time. I get rid of all the additional dislocations that were produced by the plastic strain. And then that 4% plastic strain goes to 0, because that is no longer a closed system. Essentially, you applied heat from outside to reverse that plastic deformation. But in the process, you had to consume energy that doesn't come free. That is what annealing is. Essentially, you are putting new energy into the material. That is why they take old ships, old cars after crash, and then they take them apart and melt them and they make new cars. After you melt it, again, everything is brand new. Annealing is essentially, you can think of it as melting at a low temperature, but it's a slower process.
Professor Jamal, if you don't mind, can you look at the chat box? There are
Yes.
questions.
Yes, okay. Can you illustrate application of this theory with a simple spring dashpot example? Oh, okay, so Nushad is going to present that spring dashpot example. When is your lecture, Nushad? He's presenting it on Monday.
17th.
17th. can you present the dynamic analyses with unified mechanics theory for the simple spring dashpot system?
Okay, I will include that too.
Yeah, so Nishad is going to present that on Monday at 5 p.m., right? Yeah,
Yeah.
according to this schedule I have, it says 5 p.m. How strongly can heat generated due to plastic deformation can affect failure with it? Okay, so that is a function of the frequency of the loading. If you have a quasi-static loading, the loading is slow, the heat generation because of the plastic strain or the plasticity or your loading is small. But however, if the frequency of the loading is very high and there is no plasticity, just within the elastic zone, there will be significant heat. That is an example of ultrasonic vibration. Xiaowei Li is going to present that on Wednesday, 19th. Again, during this time slot. For example, in the sample that we are testing, still, it goes to, I think, around 400, 500 degrees Celsius. Even though there is no plasticity, the strain is very, very small. It is in the elastic zone, but the frequency is 20,000 hertz. The frequency of the loading, the temperature goes to 500 degrees Celsius. So it's a completely function of the temperature, the frequency of the load. Okay, I don't want to hold you much longer. My time is up. Good night to everyone. And I'll see you tomorrow morning. Bye-bye now.
Bye-bye, sir. Thank you very much.